my pleasure to introduce Trent Guerrero. Trent comes to us from Parker, Colorado, which is, I learned 30 seconds ago, in the greater Denver area. I knew Trent came from Colorado, but now I know a little bit more specifically about where he comes from. So I first met Trent as one of my very first students here at Lawrence in my inorganic chemistry class. And I also remember he was one of the few brave students to simultaneously take Deanna Donahue's analytical chemistry and my inorganic chemistry concurrently, which, you know, anyone else who's done that can fill you in on what kind of an idea that is. And you can also look at the course catalog now and see that those two aren't even offered in the same term anymore to understand what kind of a challenge that is. So I should say Trent met the challenge aptly. He did great, I believe, in both classes, and it was fun because he got to come out to my house, not just for the end of term taco dinner that I hosted that year, but also to sample our well water and check that out for analytical chemistry. So since then, Trent and I have talked, and he's kind of a boat that I launched and just let sail to wherever it would go. I gave him some time of mine to talk about an idea of some chemistry that we would like to do, and he took that idea and ran with it. And so the molecule you see here that he's going to talk about is one of his own design, and he has largely done all of this work completely independent from me, so one of the most truly independent studies I've ever had. So with that, I'll give the floor over to Trent.
Well, thank you for the wonderful introduction, and thank you all for coming on this nice but arguably disgustingly humid hot day. So let's get into it. As you can see up on the screen already, I'm going to be talking about the synthesis that I've been doing of this redox active multi-topic ligand, and we'll get into a bit of that more. But first, we need to kind of build it up to talk about this. So the first thing we're going to talk about is something called coordination chemistry, which is one of the staples and most important things in inorganic chemistry. So coordination chemistry deals with coordination complexes. And so in coordination complexes, we've got metal centers and organic ligands. And so you can see here the M in this little red ball right here, that would represent the metal center. And then the L's around it are the organic ligands that coordinate around that metal. And what do we mean by coordinate? Well, the ligands come in and they end up sharing electrons with that metal center. There's no net change in charge between the ligand or metal, but they coordinate and they happily share those electrons. And that's what ends up happening when you have coordination complex. So a few examples are actually two different Nobel Prize winning complexes. This first one on the left, one for showing that we can get new geometries, this octahedral geometry. The one on the right was the first complex that showed that a carbon metal bond was possible in complexes. So let's go on from that. Now we've got that, one of the basic things going. So that leads us to something called metal organic frameworks, or MOFs for short. And metal organic frameworks are a subsection of coordination polymers. So you may be asking, well, and they've got metal centers and the organic linkers as well. So you may be asking, what is a polymer if you don't know what a polymer is? Well, polymers are basically, you can think of something like plastic, where you've got one single unit, or like one molecule, and then you take that and you polymerize it into a polymer, and you create long strings of that one repeating unit. So coordination polymers, you take a monomer of a coordination complex, and then you string it out. And you can do that in one dimension, and we call these, instead of organic ligands, they're still ligands, but we call them linkers now because they're linking metal centers together. So you can build this up in one dimension, you can build it up in 2 dimensions where you've got it going up and down and left and right. You can do it in 3 dimensions where it's coming in and out of the plane of the screen. So now that we've got that kind of concept down for MOFs, let's talk about some of the terminology that we need to talk about in terms of building up MOFs. So the first one would be talking about denticity. And denticity comes from the Latin word dentis, which it means tooth. So this describes the number of ligand donor atoms at a binding site that can bite on to a metal. So they can kind of grab onto that metal. So you can have something that's monodentate, like we were talking about on the last slide, where there's just the one nitrogen atom right here that can grab onto that metal. And there's just the one that grabs on right there. Now you can have something that's bidentate, like this diaminobenzene, where you've got two nitrogen atoms that bind onto the same metal. And the most important thing to think about with denticity in this regard is they're binding onto the same metal. And then you can have something like tetradentate, which is, this is actually one of my favorite ligands. It's Trent, so it's my name minus T. So you may be thinking, how can something like this end up grabbing onto the same metal? Well, the thing that's cool about Trent is it wraps around kind of like a giant claw, and they all grab onto that same metal. And they kind of just engulf that one. Well, the metal is engulfed by that one ligand. Another thing that we need to think about is obviously these are all monomers. Well, we need to get something that will create a polymer for metal organic frameworks. So we need to think about topicity, and specifically multi-topic ligands. So this is ligands that are multi-topic combine more than one metal atom. And this importantly happens at different parts of the ligand. So you can have something like we were talking about earlier with the diaminobenzene, which is monotopic, where it is just simply binding onto, it's bidentate, you've got these two nitrogen atoms binding onto the same metal, and there's only one site on the ligand that can bind to a metal. Now, increasing that complexity, you can do ditopic molecules, which have two arms that reach out and grab onto a metal on different parts of the ligand. So that's something like this tetraminobenzene, where it is bidentate still, where you've still got two nitrogens grabbing onto the same metal, but now you've got two arms that make it ditopic, and you can grab two different metals. And that goes all the way up, and you can get something like tritopic ligands, where you've got three arms that reach out. This is still bidentate, but now it's tritopic, because it's got three arms that reach out and can grab three different metals. So now we've got some of the basics on building up MOFs. Let's talk about some of the interesting properties of MOFs that we can kind of take advantage of. And as you may have guessed, one of the big ones is wide structural variety. We haven't really talked anything specifically about specific ligands and metals, and that's because you can switch out ligands and metals all over the place. So the structural variety really depends on these metals used and the organic linkers used. Just for reference, this was the image that we were using earlier. So let's look at a couple of MOFs and kind of look at increasing complexity. So this is MOF 5. It was one of the original MOFs synthesized in the mid-90s. As you can see, it quite closely resembles that same kind of just a cube, and it repeats, and then this will actually grow in 3 dimensions. So it looks almost exactly like that. Now, a quick side note on naming things. MOFs, with naming MOFs, there's not a very big emphasis on convention in naming. So if you make the MOF, you can name it whatever you want. So that makes everything really quite confusing. Like this MOF right here would be MOF 1, the first MOF made by Hong Kong University of Science and Technology. So from here on out, I'm not really going to talk about the names of the MOFs. I'm just going to point them out. It just gets confusing. But as you can see, this MOF in the middle here has a higher level of complexity, and even because of that, because it's repeating units, you can get some type of symmetry out of that as well. You can keep going along with that and even higher levels of symmetry. And so as you can see, there's a wide structural variety between even these 3 MOFs. Now, even within one MOF, you can also have wide structural variety, where here's MIL53, where at a low temperature, you've got bonds that kind of go diagonal, at least in this image. Well, if you heat that MOF up, what ends up happening is it stretches out, and then you've got these holes in the middle. And that leads us right into one of the most important and highly researched properties of MOFs, and that's the fact that they have high porosity. So you may be thinking, what is porosity? I don't know what that is, whatever. Well, porosity is the measure of the void space in a material, or void spaces in a material. And this is generally given in a percentage, so it's void volume over total volume of the material. And some everyday objects that have, or an everyday object that has a high porosity would be something like a sponge, where we've got all these little holes in the material of the sponge that is empty, and you can fit something in there. We'll get into that a little bit later. But anyway, here's MOF 5. It's a better 3D rendering of it, and as you can see, there's this big beach ball shaped thing in the middle. That is a rendering of the actual pore size of the MOF. So that's the area that there's nothing there, so we can take advantage of that eventually. Let's look at those MOFs that we were looking at earlier, and as you can see with the change in structural buildup of the MOF, you can have different sizes of pores. And then even between the same MOF, you can have different size pores within one MOF. And then let's move on to another property that really kind of goes hand in hand with that high porosity, and that would be large surface areas. Because if you have a lot of empty space, you're going to have a lot of surface area within a material. And actually, some MOFs have really absurdly high surface areas. For instance, a group at Northwestern in 2012 synthesized this MOF, and it has a surface area of over 7,000 square meters per gram. So to put that into context, if you're holding a small paper clip in your hand, that's about a gram, give or take a little bit. So a gram of this MOF, equivalent to about a paper clip. If you take that out, take all that surface area and spread it out, it will stretch over 1.5 American football fields in that one little gram. So that's mind-boggling to me. So that's something that we can really take advantage of. So now that leads us into applications specifically dealing with MOFs and using their porosity and surface area to our advantage. The big one that I alluded to earlier was actually storage. And so this is MOF 5 again. And you can actually store different gases in MOFs. Now, this is a good point to kind of differentiate between absorption and adsorption. Absorption is just absorbing something into a pore in a material. So technically MOFs can absorb things. However, adsorption with a D is the process by which some kind of molecule, ion, etc. comes in and it adheres to the surface of a material. So what's really groundbreaking about this is if you want to store a gas, obviously normally we put them in just the gas in a canister at high pressure. That's it, whatever. Well, with a MOF, you can actually, using a MOF, you can put the MOF into the canister, and then you can put the gas in there, and the gas molecules will actually adhere to the MOF structure. And because they are no longer acting as gas molecules, they won't contribute to the partial pressure anymore, and so you can store more of that gas in the storage container at a lower pressure, which has applications in a lot of fields like natural gas and plenty of other fields. So now going hand in hand with that is separation. Because we were talking about adsorption, well, MOFs preferentially adsorb different materials and gases over others. And you can use this to separate different gases in gaseous mixtures like ethylene and ethane, etc., and nitrogen or carbon monoxide from the air, and specifically carbon dioxide. Obviously, this has application in trying to collect that runoff that we're putting off into the atmosphere. So this could have some future in terms of helping mediate our CO2 emissions. Now, interestingly enough, you may think this may just be for gases. Well, just this last year, actually, the last few months, a group out of Korea was able to preferentially absorb metals with MOFs. Specifically, they used a zirconium-based MOF, and they threw it into a acidic aqueous solution containing, it was nickel, cobalt, palladium, and platinum. And when they came back, they found that the MOF actually preferentially adsorbed the palladium over the other molecules. So this it's in its infancy still, this research obviously, but you can actually use this MOF to or MOFs like it, to actually separate out ions from some type of solution, like maybe cleaning water or something, I don't know. This is in its infancy. Another talking about water, actually, let's get into harvesting. And this is specific to water, this harvesting is at least. So up until recently, the problem with harvesting water with MOFs was that once you got the water into the actual structure, you'd have to impart a lot of energy into the system to actually get that water back out and to harvest it. But in the last year, researchers have synthesized this zirconium MOF, where during the night at cooler temperatures, the MOF will absorb water adsorb water even from low humidity air. And then during the day, the energy from the sun will impart enough energy into the MOF that the water can be expelled, and then you can actually harvest it, which has applications for collecting water in parts of the world that don't have access to electricity. So this is a really big and quite fascinating research finding that they've found here. And then one more interesting application in terms of porosity and surface area would be in medicine. Until recently, most researchers have considered MOFs to be way too toxic, both the metal centers and the organic linkers, to be used in medicine. However, researchers have been looking into using biocompatible MOFs that they've actually been able to encapsulate drugs with and use as delivery systems. Specifically, researchers, I think it was about 2010 or 2011, managed to synthesize this MOF, CD-MOF1, CD standing for cyclodextrin, which is a sugar that is enzymatically produced from starch. And they did multiple different syntheses of this MOF. And then from that step, they were like, well, let's see if we can incorporate drugs into it. So they incorporated ibuprofen, which most, if anybody, has heard of, or used, probably. And so it has a wide application. And what they found is that when they incorporated it into it, and they tested it on cells to do an in vitro study, they found that up to about 100 micromolar, there was no effect on cell viability, no toxicity whatsoever. So then from this step, they went on and they did in vivo studies with mice. And they found that when they were administering ibuprofen in the CD-MOF, the blood plasma levels of ibuprofen reached the same concentrations at the same time as our everyday ibuprofen salt, but the half-life of the ibuprofen drug was actually increased by 100%. So rather than taking the drug that we have normally over the counter, where it's just the salt, you can actually, instead of taking it 4 to 6 hours, if you have it encapsulated in a CD-MOF, you can take it every 8 to 12 hours, which has very big precedence in terms of future research with drug delivery. And other researchers have actually been doing this with other biocompatible MOFs and incorporating things like aspirin and ibuprofen. And there have been even studies talking about using anti-cancer drugs encapsulated in MOFs and using those as delivery systems. But this is still quite in its infancy and hasn't broken out into pharmaceutical land yet. So that's the end of the digression in terms of porosity and whatnot. Let's get back to talking about the thing that I find interesting from my research. And that's dealing with the properties of the polymeric nature and structural rigidity of MOFs, and specifically as their potential use for electroconductive properties. And as of about 2012, chemists were still questioning the conductive nature of MOFs. Before 2012, there had been a few studies on things like MOF5, and they had shown small conductivity levels, but not enough to be worth looking into. But as researchers do, they looked into it more. And they found that, and specifically, they found that some MOFs can be used as semiconductors. And use as semiconductors really depends on the building blocks, like all the other properties previously, the metals and the ligands. However, as you may know, a lot of transition metals are great conductors, but why don't all MOFs conduct electricity then? Well, that's mainly more dependent on the ligands used, because if the metals can conduct and the ligands can't, then the whole material cannot. So specifically with the ligands, we have to think about pi conjugation, about potential band gaps, and then also dealing with redox activity. So now we're going to hash out those few topics real quick. So pi conjugation, for those of you that kind of forget your Gen Chem terminology and whatnot, let's talk about specifically just the simple benzene, which is a 6-membered ring that's got your alternating pi or double bonds. So normally with a single bond, you've got a direct interaction. That's why the single bond is the strongest bond, because it's got the most overlap of orbitals. Well, with double bonds, since something's already taking up that space in between the atoms, you can't really make a bond that way. So what ends up happening is you've got these p orbitals that stick up and below the plane of the ring or the atoms. And what happens with the double bond is those p orbitals will end up interacting side to side, and then they'll form an orbital that way. And when you've got something that we would call conjugated or alternating double bonds, they end up forming these orbitals that overlap the entire ring. And then electrons can flow in that ring quite freely around between atoms. So now if you've got something like a polymer of benzene, I don't know, polyphenylene, that's going to have long sheets of conjugated or pi conjugated orbitals going along that polymer. So that's important to conductivity. So let's talk about orbital energies now. That's the other thing we need to think about. So without going too much into molecular orbital theory, because that's a whole other topic in the presentation, let's talk about the simplicity or the simple topics of orbitals. So let's think about something like benzene again, where chemists like to think about orbitals as having discrete energies. So you've got your single bonds are way down, way below, like on the first floor of the building. They're way down there because they're very stabilized and the electrons that are there are very happy with being in that orbital. Well, these orbital lines represent the pi orbital, so that double bond, and then when orbitals mix and form molecular orbitals, they split, and you've also got a pi star band, or orbital. So, as you can tell, there's a large energy gap in between these, and that is really why electrons would rather be down here and they can't really go up to that pi star, and that's why we would call it something like an antibody. And once you have a lot of these benzene molecules together, these orbital energies end up kind of conglomerating together into something that we call bands. And that leads us directly into band theory, which is specific to solid materials and deals with the energy levels populated and unpopulated by electrons. And specifically, we'll be talking about the conduction band and the valence band. Those are the two bands that we're really thinking about. And before we go in any more depth, I'd like to just explain the difference between conduction band and the valence band. So electrons that would be in the valence band will have lower energy and they'll be associated with a specific atom. They'll be in those valence orbitals. Now this is technically wrong, but this is an easier pictorial version of it. And then conduction band electrons will be the ones that are floating around, not associated with any one specific atom, but they're floating around between the atoms. And that would be where electricity can flow. So now let's combine that knowledge and the conduction valence band with the previous bands that we're talking about and labeling them. So this is a representation of an insulator. So insulators are things like wood, glass, rubber. They don't conduct electricity. And that's due to the fact that they have a large band gap, a large energy difference between the valence band and the conduction band. So to get an electron up into that conduction band and to start conducting electricity, you need a whole lot of energy to push that thing up there, which is not very practical, and that's why insulators don't conduct electricity. On the other end, we've got conductors, where they have little to no band gap or even overlap between the bands. And that means that electrons can freely flow between those two bands, and that means conductors like metals and other things can end up just conducting electricity on their own. Can't really control it, but that's just what they do. So now we need something in the middle that's not completely always conducting electricity, but can also control and will conduct electricity. And that something is semiconductors, where they have a band gap. It's a small band gap, small enough that it's big enough that it'll keep electrons down in the valence band, but if it's small enough that if we put in a little bit of energy, like flip a switch and put a little bit of energy in, those electrons will go up to the conduction band, and this material will start conducting electricity. And that's really where metal organic frameworks and coordination polymers come in, because a lot of them can work really well as semiconductors. One more thing we need to think about in terms of conductivity is redox chemistry. So for those of you that forget your Gen Chem redox chemistry, let's go through that really quick. There are two parts to a redox chemistry reaction. They go hand in hand, and it deals with, and the reason why there are two parts is because it's dealing with the transfer of electron. So obviously if one is losing an electron, another has to gain an electron. So we call these reduction, which is for the gain of electrons, and oxidation, which is for the loss of electrons. And a quick terminology thing, if something is being reduced, it is being reduced by a reducing agent, but that reducing agent is itself getting oxidized. So terminology, that'll come up in a second. So let's take a look at a normal redox chemistry reaction with plain everyday ligands in a mod. So you've got your complex sitting here just kind of floating around happy. The metal's got the coordinated ligands and it's got its electrons. Now an oxidizing agent will come in and it'll swoop in, steal an electron from the metal, and then take it away and change the charge state of that metal. Now, this is what we would normally call a metal-centered redox reaction. That's normally how these things happen. Now, let's talk about something called redox active ligands. That came up at the very start. They're also known as non-innocent ligands, and these ligands have more energetically accessible levels that they can access that allow them to actually participate in redox reactions instead of just the metal interacting in these reactions. So let's look at this from this standpoint, where we've got redox active ligands now instead of non-redox active ligands. So your oxidant is going to come in, it wants an electron, It's going to come in, but instead of stealing it from the metal, it's going to steal it from one of the ligands, or multiple of the ligands, depending on how many electrons it wants to take. And that will change the charge state of the ligand and not the metal, and the metal will not change at all. And this is really the precedent for electroconductive MOFs, because now you can put in ligands that also participate in redox reactions. So sometimes this will happen, and sometimes the metal will donate the electron. And that's what turns plain MOF into something that can conduct electricity. So now let's look at a few applications, and this is really how I got introduced to a lot of this stuff in my research, and specifically with sensing technology. And researchers have been looking into using MOFs that are graphene analogs for sensing technology. You may be asking, why don't we just use graphene? Or what is graphene? Well, graphene is made up of these 6-membered rings that are conjugated, and it makes up one giant sheet. And obviously, if we think back to the pi conjugation slide, this has those bands over them, or the orbitals below and above the ring, or the sheet, so that it can conduct electricity quite well. However, the problem with graphene is, especially with sensing technology, is if you have an analyte come in, it'll interact with those carbons in the sheet, and it'll disrupt the pi conjugation, and it'll also disrupt and interact with the conduction band and the valence bands, and that'll end up stopping the flow of electricity around that specific carbon atom. And if you have enough analyte come in, it'll completely stop the flow of electricity. So you're technically sensing something by stopping the flow of electricity, but you can't really tell how much. It just says that it's there. So it has application, but not a whole lot. Well, researchers have synthesized this ligand, this redox active tritopic bidentate ligand, HITP, which we saw earlier, that's why I pointed out. When you actually take this ligand and you throw it in with a metal and make a MOF, it creates a macro version of graphene, where it'll also form sheets. It's obviously a lot bigger because these are the same rings as right here. But this MOF specifically with nickel in it has actually been a record-breaking MOF in terms of conductivity for MOFs, and it stands up there with semiconducting organic semiconductors. And it doesn't really compare in terms of conductivity to graphene, but that's because graphene has a high conductivity, but it's not completely applicable in terms of using it in technology. So thinking about all of these things that we've been talking about, denticity, pi conjugation, band gaps, redox activity, that all of this background research kind of came together in terms of my proposal. And I had to think about, well, we need something that's conjugated. We need something that's got, that's flat, could possibly be redox active, and also something that's bitopic or tritopic. And that led me to coming up with this design, which after a couple of different rehashes of it ended up with Phenazinetetraamine. Now, I didn't just sit around at the computer and do a bunch of research and then draw this. I actually went into the lab and did a little bit of research. So let's talk about the synthesis real quick. We ended up starting with the 1,2,4,5-tetraminobenzene and sodium acetate, grabbed a 3-necked flask, throw them in there with each other, and then with a little bit of water. And then before we can actually run the reaction, we need to throw a glass stopper on this neck, because we don't really need it. Throw a condenser up on the top one, we'll get to that in a minute. And then a rubber stopper on this third neck, which is important because that's where we're going to put in a needle and then flow air through the plasma reflux. Now, for those of you that don't know what reflux is, it's basically like using a slow cooker, kind of, where you throw it in there and you just kind of let it simmer for a long time. And I let this reflux for 5 hours, so it's very similar. But this condenser up on top is kind of like putting the lid on the slow cooker, where you don't want the reaction or your food, whichever one, to dry out. So we flow water through this, cool water, and then any vapor that comes up will condense on the inside of this tube, and then flow back into the reaction so we can keep everything in there. So after we ran the reaction, I let it cool, and then I vacuum filtered it for a while, and I ended up with this gorgeous black powder. It's actually not completely black, it's partially purple, it's really hard to see in this picture. So yeah, so now from this step, how do we know we didn't just throw in our starting reagents and let them boil in water for a few hours and then filter them out? Well, we can do something called a TLC plate, which deals with comparing the polarity between our between the starting material and our products. And TLC stands for thin layer chromatography, but we'll get to that in a second. So we're dealing with the polarity. And specifically, polarity deals with the charge distribution in a molecule. So a good example is something like water here, where we have our two hydrogens and our oxygen. And the oxygen is extremely electronegative, and it likes to pull that electron charge or distribution cloud, whatever you want to call it, towards itself. And that ends up making this center portion where the oxygen is quite negatively charged. And then the two hydrogen ends are positively charged. And what ends up happening is something that's polar can end up, well, not coordinating, but they interact with each other. And with water specifically, you can get hydrogen bonding. And that's what ends up giving water its high surface tension. So with a TLC plate, let's kind of look at the data and we'll go from there. So with this, what you do is you dot your samples on each of these. And we've got one here is our starting material, and 2, 3, 4 are theoretically could be my product. That's just the products from 3 different reactions that I ran, the same reaction. And as you can see, this dot right here is not nearly as high as the other 3. And that's because we'd expect the starting material to be quite a bit more polar and interact with this. It's called thin layer chromatography because there's a thin layer on the plate that is polar. So something that is more polar will not travel as far because it'll get stuck on that plate, whereas less polar things will travel farther. And this is encouraging because we would think that this would be more polar because the charge will be pulled towards those nitrogens and away from the middle of the ring, whereas with our theoretical product, they'll be pulling the charge away, but then there's these nitrogens in the middle that will kind of even that out. So now that we've figured out we haven't just filtered and isolated our starting material, how do we know what we actually make? Well, that leads us to HNMR. And for the P chemists, I'm sorry, it's going to be a really short, short introduction to NMR in terms of we throw our sample into a magnetic field, and isotopes of, specifically in this case, hydrogen will end up interacting with that field, and then when you turn that field off, they'll relax down, and that'll be something that we can measure and identify in terms of the chemical environment around that specific isotope, in this case, hydrogens that we're looking at. And then we end up getting something with some peaks, and what we call this is to your left would be downfield shift, or a chemical shift, and then to the right would be a more upfield chemical shift. So let's kind of examine this really quick. So this peak over here, I've determined that the one peak right here represents all of these 4 red hydrogens, and that's because they're all in the same environment. They're all in between these 2 nitrogens, and so they're all going to be interacting with that field in the same way. Subsequently, I also kind of identified this weird little mound thing as possibly being these hydrogens around here. That I'm not sure about, but that's for future work. And then you may be asking, but what about these giant peaks over here? They're like the more interesting ones. Well, I've determined this one to be excess water that couldn't actually get out of the material yet. And then the last peak is actually our solvent peak, the deuterated DMSO. So now, that's about as far as I got in terms of in-lab stuff. So now we can think about the future work, the next few steps that we're going to actually take with this research. And first and foremost, we want to take that water out. We want to be able to take that water out and really analyze just our product. Another thing that we could do after that is electrochemical analysis, specifically chemical analysis on the ligand itself. And then we could cap that ligand with some type of metal cap where the metal is bound to something that won't allow it to form a polymer. And hook that up and see if that'll have any type of electrical properties, any band gap, et cetera, et cetera. And then the end all be all goal would be to actually create a MOF out of it. Something like, I don't know, this with nickel in it. Throw in either nickel or copper because those seem to be the most conductive in terms of incorporation into a MOF. And see if this is actually a redox active ligand that contributes to a high conductivity in this MOF. So that's about where the research is at right now. And so thank you. I'd like to give a few acknowledgments. Dr. Dave for dealing with all my stuff these last 5 years, running across college constantly and scheduling labs with rehearsals and whatnot. And then with Graham, when I managed to frantically email him this summer and say, can I please do research? And he's just kind of like, sure. And helping me out through this entire process, entire chemistry department for helping me be able to understand all of this. And then also DMAR for dealing with me when I come down from the lab, asking for a bunch of stuff all the time. And then also friends and family who really helped me get through all of this in my 5 years here at Lawrence now. So, thank you.
Questions?
Obviously, it will kind of depend on the moth, but how like cost efficient is making like a moth? Like how expensive is it to make something thinking like a biomedical?
Yeah. Well, I mean, obviously with the cyclodextrin moth, they actually use Everclear, potassium hydroxide, and just cyclodextrin sugar. So those are really cheap. There obviously are, depending on the ligand that you want to build, it can be quite expensive. Our ligand, depending on the starting products, it was more expensive to just buy, because this molecule exists that I was creating. It's a lot more expensive to just buy that than actually go through the synthesis and make it. So it really depends on where you want to start, how fast you want to get to your end result.
How might you dry that product?
I was thinking, well, Graham suggested either Schlenkline or vacuum oven. That was something that I found in a couple of sources where they use a vacuum oven to dry it. Apart from that, I'm still looking into it.
A rough and dirty way to do it might just be to dissolve in toluene.
Okay, yeah.
And just stir that.
Follow-up question to the water question. Usually when you have water in an NMR sample, it's a really huge, broad, weird peak, and this is just needle sharp. Why?
I'm not sure.
I throw that out there. I thought that was
It
kind
doesn't
of...
look like that much water for being in here, so.
That's the point.
It's just not much.
No, it's even.
Oh.
Yeah.
Have you considered trying to use another solvent?
I considered, yeah. And I was just using the DMSO because that's what multiple sources have used. But I've considered trying another one.
Yeah, it's not at all surprising if NHs won't show up in DMSO, but if you use another solvent.
This question on the shape that you can make with the ligands you were trying to use. So given that you just basically got like almost a moth wire, I think, how would you have any sort of control about the directionality that this kind of monomer unit could build?
Well, it's not really going to be able to build up or down because you could bite on here, but it's going to preferentially bite on here. Okay. So it'll end up creating a long string. And theoretically, you could use this more in terms of like a film on a surface rather than building it. Because this is not going to be exactly three-dimensional. It's going to be basically one-dimensional. It'll be a long string.
Right. So would it be potentially used, could you then use it for molecular wires and molecular conduction?
Yeah, on the macro or on the micro scale, you
Right.
can probably use it as that.
Cool. And then another question, is it possible to do, if you had two types of linkers or two types of ligands, could you do some kind of we're going to use the term block copolymer to kind of create this part's doing this, has that structure, and then you have another one, so this nickel's going to, dentate over something that goes that way or something. Would there be a preferential trick?
You could, I think the way to go about that would be to maybe include some kind of metal cap and then create a moth from that, and then maybe try and get that cap off and then grow something on the other end.
That sounds hard.
Yeah. That's my only way I'm thinking of right now that you can get around that. Other than that, the thing about moths is you kind of throw them all together, or throw the metal and the ligand in, and it kind of builds itself. So it's not exactly, you can't really go out and say, I want this ligand here and this ligand here. It'll do it in a way that's most symmetrical and easy to, it does it itself. Basically.
So maybe another way to ask that, have you ever seen an alternating polymer like this?
I've seen some moths that have different types of ligands in them in the same moth, but it's really difficult to try and get that specificity where you want it to alternate or something like that. It'll,
Sure, but there's some precedent.
there's some precedent there. That's obviously where research is going, is looking into having multiple different or ligands in a MOF and that applicability.
Okay, there's no more questions for Trent. Let's do one more time.